Okay, so now let's take a look at specifically how to create a confidence interval for a proportion. So we're going to do these inferences, which means a confidence interval in this case, specifically for proportions. Now, extremely important concept. I said this earlier, and I'll say it again. A confidence interval is always, 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 always about the population parameter. It's used to estimate the population parameter. It's never used to estimate the sample statistics. So that doesn't even make any sense when you stop and think about it. Why would you ever want to estimate a sample statistic? You know what it is. You just calculated it from the sample data. It's a population parameter that you don't know. That's what you're trying to figure out. So a confidence interval is always about estimating the population parameter, and the way we estimate it is based on the sample statistics. Now, recall from the previous chapter that under the right conditions, we know that p hat, the sample proportions, are distributed normal with a mean of pi and a variance of pi 1 minus pi over n. So we're going to need this information. So as a quick review, what are those conditions? Well, the first condition is that I need n times pi to be at least 5. The next condition is n times 1 minus pi. That needs to be at least 5. And the last condition, which is not all that important, I said it earlier, you need to check with your professor, because personally, I prefer my students to completely ignore this next one, that being n of at least 20. Like I said, I definitely prefer my students to just pretend like that never even happened, but some professors do require that, so you should check with your professor and see what they do and don't want. So if we show these conditions are reasonably satisfied, which this is just simple mathematics, a little bit of algebra, then we can say that this is probably true, and we can use a normal distribution. Now we can use this knowledge to help build a confidence interval for pi. Now the general form of the confidence interval, as a reminder, is the point estimate plus or minus the margin of error. Now the margin of error is determined by a combination of a couple of things. First of all, the level of significance. Now the level of significance, I'll talk about more just a little bit, but remember earlier I said that a confidence interval is built with a certain level of confidence, a certain confidence level. Well, the confidence level and level of significance go hand in hand with each other. So those are extremely important. The other thing that determines it is the sample size. And we can see it right here because this piece is the variance, and right there is the sample size. And for proportions, the sample proportion is also needed to determine the margin of error. Now, let's take a look at this real quickly and see what we've got. A confidence interval for pi should look like p hat, there's my point estimate, plus or minus z, and the subscript here, in case you can't see it very clearly, is alpha divided by 2 times the square root of pi 1 minus pi over n. And this piece right here is what we call the margin of error, which we very commonly abbreviate ME. So let's break this down piece by piece and see what this is. What is pi 1 minus pi over n? Well, that is the standard deviation for pi, because the variance is right here. If I take the square root of this, if this is the variance, the square root of the variance is the standard deviation. So that's what this piece is. So I'm adding and subtracting z of alpha over 2 times the standard deviation. Well, what is z of alpha over 2? Well, if you recall, z is from the standard normal, right? So we think of a z-score as the number of standard deviations away from the mean, correct? That's the basic definition of a z-score. So what is z of alpha over 2? Well, I'm going to have to talk about this alpha now and tie it in with the level of significance and a confidence interval. The level of significance is represented by alpha. The confidence level equals 1 minus alpha. These two work hand in hand together. So as an example, if I said my level of significance is 0.05, so alpha equals 0.05. 1 minus 0.05 equals 0.95. That means that alpha of 0.05 gives me a 95% confidence interval. If I use a significance level of 0.05, then I'm going to be able to say I'm 95% certain that the true, in this case, proportion falls in the confidence interval. If I let alpha be 0.02, 1 minus 0.02 is 0.98, I'll be 98% confidence. Well, why do we need these two notations? Brings me right back here to z of alpha over 2. So if alpha is 0.05, then alpha divided by 2 equals 0.05 divided by 2, which equals 0.025. Now remember, the normal distribution is symmetric. So the z of alpha over 2 says, in this case where alpha is 0.05, I need a z-score out here someplace, a value of z, that gives me alpha over 2 in the tail, which in this case is 0.025. So for sake of conversation, let's just pretend like that value of z is 2. Remember, this is 0. Standard normal is centered at 0. Right there's the mean. Well, if I go 2, positive 2, I have 0.025 in the tail. If I go negative 2, down here to negative 2, I will also have the same alpha over 2 in the tail. In this case, it's 0.025. Clearly, as I change alpha, the amount in the tail would change, but the concept is the same. So if the value of z that gives me half of the level of significance in the right tail happened to be 2, that means I would need to go 2 standard deviations away from the point estimate. Well, this is the standard deviation. Multiply it by 2, add and subtract it from the point estimate, and that's what I'm going to build my confidence interval on. It'd be based on taking my point estimate and going 2 standard deviations in each direction. Now in reality, it won't be a 2, but it's going to be something very close to that if alpha is 0.05, and this value will change as the level of significance changes. Now using this, and this should have a square root on it. There we go. Using this creates a serious problem, though. I mean, this is the basic idea. This is exactly what we want to do, but we can't. This is a very serious problem. And the hint here, in terms of what the problem actually is what is it we're trying to estimate? Oh, we want to estimate pi. But what's right smack in the middle of our calculation? Pi. So according to this, we have to have pi before we can estimate pi. That doesn't make any sense. So what we do to avoid that problem is we use sample statistics. So our confidence interval for the proportion will look like this. P hat plus or minus z of alpha over 2, this z has not changed, times the square root of, we don't know pi, but we can estimate with p hat, 1 minus p hat divided by n. Okay, once we do that, these assumptions before, we said number 1, we had to have n times pi had to be at least 5. Number 2, n times 1 minus pi had to be at least 5. Well, those don't make any sense anymore because we no longer have pi. So instead, what we do is we say that this assumption that p hat is normal is reasonable if both the number of successes and the number of failures is at least 5, and the sample size is at least 20. And again, that 20, for my students, ignore that. All we want is the 5, but once again, you should check with the professor if you're not in one of my classes to see what they want you to do with that. Okay, so mathematically, what we're saying is the number of successes, n times p hat, has to be at least 5. Well, why is that the number of successes? Well, if we think of a sample proportion as being x over n, where x is like a binomial random variable, in that it has a number of successes. If you're looking at a proportion of males, x would be the number of males. If I take p hat and I multiply it by n, on this side the n's going to cancel out, and all I have left is the x, the number of successes. Likewise, if I take n times 1 minus p hat, that also has to be greater than or equal to 5. Well, 1 minus p hat equals 1 minus x over n. And if I multiply that on both sides by n, the n will cancel here, it distribute here, I'll have n minus x. Well, n minus x plus x is going to be n, so n minus x is the number of failures. So in other words, if I had, let's just say n equals 100 and p hat equals 0.7, well that's 70 over 100, so I would have 70 successes. That means 100 minus 70 is 30. That's how many failures I would have. That would be my n times 1 minus p hat. So let's go ahead and take a look at a quick example here and work through this process to make sure we can put all these pieces together. So, campus administration is proposing that classes which meet 4 days a week be changed such that they only meet 2 days each week, but for a longer period. The proposal suggests this could increase the number of classes available to students, allowing them to complete their degrees in less time. A survey of 137 randomly selected students was asked if they were in favor of the proposal. Of the 137 students surveyed, 114 said they were in favor. Estimate with 95% certainty the true proportion of students on campus who are in favor of the proposal. Now, here's a few things I want to do. I have it numbered here. This is basically my thought process whenever I deal with situations like this. First thing I want to do is identify the parameter of interest. What am I talking about here? Well, I'm talking about proportion. So the parameter of interest will be pi, which is a proportion. This is actually extremely important. It may seem kind of silly to you, but it's extremely important because we're about to do the mean and the median. Those techniques are different. We don't want to get confused. By starting off and identifying the parameter that we're talking about, that will help direct us in the right direction. Now, I want to identify the probability distribution to be used, addressing all applicable assumptions and how they're satisfied. Well, what I want to do a confidence interval for the proportion is I need p hat to be distributed normal. Okay, well, I need to find some stuff here before I can figure that out. Well, what is p hat? P hat in this case, they said n was 137, and 114 said they were in favor, and they want to calculate the confidence interval for proportion of students who are in favor. So this is going to be 114. So that's p hat. That means that there's 140 or 114 successes. So n times p hat equals 114, which is clearly greater than or equal to 5. So we're good to go there. So 1 minus p hat equals 137 minus 114, which is 23. That is the same as, well, n times 1 minus p hat. I'm going to end up with 23, which is also clearly greater than or equal to 5. So this is the assumption, and this is how we know that the assumption is reasonably satisfied. Now I need to construct my confidence interval. Well, it's said to be 95% certain. That means that alpha, the level of significance, equals 0.05, and the confidence level equals 0.95. So my actual confidence interval will look like the point estimate, which is 114 over 137 plus and minus z of alpha over 2, which we haven't found yet, times the square root of 114 over 137 times 1 minus 114 over 137 all over n. Now, I'm going to jump to TC stats here in just a second and show you how to find this z of alpha over 2. I'm going to start off with a quick picture. Alpha was 0.05. That means I have 0.025 in the tail. That means that I have 0.975 in this side of this boundary. That means this is P of 0.975. This is the 0.975 percentile. And that's how I can find that value of Z. So in TC stats, if I select analysis method without data, and then go to probability distributions, and then go to the normal distribution, on the bottom down here, you can see the inverse normal. And for Z distribution, the mean is 0, the standard deviation is 1, n is 1. This is for the Z distribution, not my proportion. And the percentile I want is 0.975. Calculate, and the value is 1.96. That means this confidence interval right here needs to have 1.96. Now, if you do all those calculations, and n, I need to change n. I don't know why I wrote n. I know that n is actually 137, so that should have been in there. Now, if you do that calculation, you're in good shape. You have your confidence interval. Now, fortunately, we're not going to have to do that because TC Stats will do this for you. I wanted to walk you through this process so you get an idea of what's going on behind the scenes. So once again in TC Stats, I'm going to select Analysis Methods Without Data. Go to One Sample, and where it says Z Proportions, I will select Z Proportions. Now this screen may seem a little bit confusing to you. There's a lot going on here. This piece right now, up here, we'll completely ignore that. That's actually coming up in a future chapter. The rest of this, all we're going to want is the confidence interval part of it. So what's the confidence level? Well, the level is 0.95. And here it says P, and that's what TC Stats use for December proportions rather than P hat. And that was 114 over 137. Now, if you had a decimal value, this proportion is actually close to 0.83. So if you use a decimal value of 0.83, you could leave this blank and put 0.83 here, but then you need the sample size of 137 here because it needs to recreate this. If you have a proportion that's set up like this as a fraction, use it. Because as soon as you do a decimal, you're going to end up doing an approximation. You're going to have some rounding error, and we don't want to introduce rounding error any sooner than what we absolutely have to. Now when I tap on Update, I see the pieces that I need. The sample proportion, remember I said is about 0.8321, rounded at 4 places. And this is my confidence interval, 0.7695 to 0.8947. So the confidence interval, if I were to actually do all that by hand, would be just what we had within rounding, 0.7695 to 0.8947. So now I can interpret the interval in English. What does it mean? What it means is we are 95% confident, or you can say certain if you like the word certain better, that the true proportion of students in favor of classes, I'm going to say 2 days a week, is between 76.95% and 89.47%. That's how you interpret this in English. Now, what this confidence interval did for us, if we would have just simply reported that 83.21, so 83.21%, if we would have simply reported that 83% approximately were in favor, that would sound like, man, that is just really, the students really want this thing. But because the sample size was big enough, the margin of error was pretty small, and that allowed us to have a confidence interval that was reasonably tight. It's not super tight, but it's reasonably tight. If I take 89.47%, subtract from it 83.21%, I'm going to get about 6.2%. So my margin of error is actually about 6.2%. Now the key here is with this margin of error, I have my point estimate, which is right in the middle. Here's my 0.8321. When I add this 6.2%, I end up at 89.47. When I subtract it, I ended up at 7695. Now, the reason this is so useful is that the lower bound is dramatically greater than 50%. So there's really no doubt in my mind, assuming my sample was reasonably representative of the population, there's no doubt in my mind that students would be in favor on this particular campus of this particular proposal. Now, one more quick thing here before I wrap this up. This is what the confidence interval is going to look like. P hat plus or minus z of alpha over 2, square root of p hat 1 minus p hat divided by n, the sample size. What I want you to see is that this value here, z of alpha over 2, that's fixed. As soon as you give me alpha, that value of z is there. It's just fixed. So what can we do to make the margin of error? Because remember, all of this is the margin of error. How can we make the margin of error smaller? In that last one, if it was 83% plus or minus like 30%, we would have might have some issues. This is way too big of a margin of error to be of any use. So if our margin of error is too big, how do we make it smaller? And the only way to do it, well, I shouldn't say the only way, but the most obvious way is to increase the sample size. Because as n gets bigger, the margin of error gets smaller, holding everything else constant. The other thing that I could do is change the value of alpha. Because on this curve that we did, the normal curve, if alpha is 0.05, then alpha over 2 is 0.025. So this would give me a value of z, which we say is 1.96. But if alpha were 0.10 divided by 2, that's 0.05. See, if this is 0.025 in the tail, then I'm going to have a value over here someplace smaller than 1.96. That will give me 0.05 in the tail. Well, if I make this value smaller, the confidence interval will be smaller. If I make this value bigger, the confidence interval will be smaller because the ratio of two numbers gets smaller as the denominator gets bigger. So the sample size n has a direct relationship on the margin of error. The two things that really have the major direct relationship is n and alpha.